Yeah.
Good. So the last talk in this session will be about, well, my personal favorite topic right these days, higher order mathematical operational semantics. And Sergey is going to talk about how to make big steps in this setting.
Yeah. Hello, everyone. Do you hear me well? Yes? Okay, thank you. Thank you, everyone, for coming. Indeed, this is going to be a talk about big steps in higher order mathematical operational semantics. More precisely about an abstract connection between big step and small step. This is joint work with Pouya Partow from the University of Birmingham and Stelios Tsampas from the University of Southern Denmark. So, and I would like to give a little bit of context to this work. So it's basically part of a bigger effort which started in 2023. Where we introduced a notion of a higher order mathematical operational semantics, which builds on a previously known notion of just an ordinary mathematical operational semantics, which can now be called first order, which has been introduced in a seminal paper by Pouya and Plotkin. So we extended that work by a certain ability to model higher order languages. And so this has sort of opened a door for a certain meta reasoning about operational semantics within a category. So, and subsequently, we developed this approach in a range of papers. Last of those being, except this present one, also the last one in this list, which has been presented by Henning today. So if you have been to the morning session, you might notice that this is related. So in a nutshell, so what is it all about? Very conceptually, we are aiming at making operational semantics more mathematical. So, and this was also the original motivation by Pouya and Plotkin. The main idea here is like to consider an operational semantic as a sort of input, like a set of rules, and using abstract methods, using the language of category theory to first obtain a categorical abstraction induced by these rules, and from those devise method and properties. So just as an example of methods, these are some sort of abstract notions of logical relations or abstract house method, other things, and what I mean by properties is some sort of compositionality, safety, adequacy, and most of the papers in this list from the previous slides, they are addressing really complicated things like proving congruence of the contextual equivalence. So in this concrete work, the issue is much simpler. It's just equivalence of big step and small step, but it's also an illustration of this general idea of obtaining something general through abstraction. So, and a nice side effect of this approach is that since it's modeled categorically, a side effect of this, it also tends to be translatable into some sort of functional implementation in functional languages or in proof assistance. And this is exactly the case for this work. Indeed, the paper comes with an artifact which implements most of the things that I will be talking about. So I could actually have given this talk completely differently, just like some kind of implementation talks and talk about type classes and functions and so on. But I choose to present it using the more versatile language of category theory. So I will explain you the problem by example. First I would like to show you this concrete example, which we like, in particular because it's very nice to illustrate derivations and like operational semantic derivations of a higher order language. So some of you might be familiar with the combinatorial logic. It's a certain flavor of combinatorial logic SKI, where we have three combinators. They correspond to certain lambda expressions. And this language of combinator being so concise, still computation equivalent to lambda calculus. Yeah, so we have a couple of non-standard features here, and that, in particular, that certain combinators have variance. So this K combinator, which is standard, stands for constant, but we also have K prime, and this is because the K is binary, but we would like to model the situation when it consumes one argument, and then it's in the position to consume another argument. So when this happens, we have this intermediate combinator K prime waiting for it. Another non-standard feature is that these labels, so labels consume, indicate an argument will be consumed at this stage. So it's a mild variation of combinatorial logic, and one can see easily that you can model transitions of the original combinatorial logic in this way and the other way around. So this language is very simple, it's purely algebraic, and it's higher order still. And it's well suited for presentations because of its simplicity. So of course, the problem is here, you might wonder, well, okay, what's about lambda calculus? And yeah, that's still been just as powerful as not lambda calculus. And lambda calculus just adds some layer of technicality on modeling name binders. And so that's why it's not optimal for presenting the main idea here, but bear with me. If I have time, there is a slide in the end about it. So we can define big step semantics for this little calculus that would look roughly like this. So we need a notion of value. We can introduce it by a grammar. So a value will be something that has a constructor on top of it. And we have the evaluation relation, which relates a program to a value. It's supposed to be derivable in this very simple system, which would mimic the corresponding big step semantics in simply time lambda calculus. And okay, so what the rest of the talk is about is this equivalence theorem, which basically states that small step semantics is equivalent to big step semantics in this particular sense. And so the question is, can we do this abstractly on the meta level, ranging over all possible rules? And a sub-question of this, can we make sense of it? Because before proving it, we need to interpret all these components in this equivalence. So yeah, this is what the rest of the talk will about. Just to avoid confusion, I will reiterate it here. And let me first explain this general notion of abstract higher order GSOS. This is done, this is formulated using very rudimentary parts of the category theory. So I will not need more than the notion of a functor, a notion of natural transformation, algebra, and a monad. I don't even need all algebra. Mostly what I need is the algebra of terms. So I will need to fix some kind of signature, which is a functor, and terms in the signature are free algebras with respect to a given set of variables. So, and in Haskell, for example, it would be an inductive type. And we will use this notation for terms without variables. So we also will need monads, natural transformations. You can just think about them as polymorphic functions if you're not familiar with natural transformations. So another slightly less familiar notion from category theory is really the final one. That's a notion of dinaturality. So dinaturality is some generalization of naturality. It works, well, it's invented as a generalization for functors of mixed variance. So it's a functor with two components. You can think about them like input and output. And so like saying that they are natural in some sense with respect to this argument amounts to commutativity of this diagram. And the prototypical example of such dimensional transformation is the evaluation morphism. So there are like two occurrences of x, input and output, and to say that we are sort of natural in them, but technically speaking dinatural, we need to make sure this diagram commutes. And this is like a prototypical example. By composing functors based on this example, we can generate more dimensional transformations. Okay, that's that. And then, so what is a higher order abstract GSOS? Like I said, the idea comes to this paper towards a mathematical operational semantic Turing Plotkin, sorry. And in our case, we generalize it. I highlight in green what is added on top of it. So we fix a signature in a standard way. Then we define a functor, which is called a behavior functor, and it models the transitions in the operational semantics. So what we add is this contravariant part of the functor, which correspond to labels on the transitions. And also, the main ingredient is this family of functors, which is natural in Y, just like in the sense of this paper, but it's also dinatural in X. And for combinatorial logic, how this is instantiated, so we take as a category the category of sets. As a signature, we just take the algebraic signature of the combinators, and as the behavior, so this is precisely a direct product of two relations. One is unlabeled arrows, and one is labeled arrows. And now you see why we need the this exponent, because we consume an input which is comes from the label of the arrow, and this input corresponds to this x here. And raw, so this is the most complex part. It's this natural transformation, which is induced by the operational semantic rule. I will sketch very briefly how this is how this works. So, for example, if we take these two rules from the semantics of combinatorial logic, they will generate this raw of this form. So now I expanded the functor, and so this green is, for example, this corresponds to the original term that we are reducing. But in addition, we can use on the right-hand side at the bottom of the rule the successor of one of the subterms, and these corresponds, for example, to these positions and this natural transformation. Or if one of the premises transits via a labeled arrow, this corresponds to this position, and this also can be used. So if you spend enough time on this, you might see how we can transform rules to this natural, dinatural transformations. And this is the first step in this abstraction process. So we starting with the set of operational semantic rules. We can define an abstract HO GSOS. And by generalities, we can, for every such HO GSOS, derive what is called operational model, which abstracts derivable transitions for every term. So for every term, we can find a successor, which is the derivable one in this deductive system for operational semantics. And this is defined abstractly using the fact that the algebra of term is initial. So for combinatorial logic, this operational model, well, it does what's expected. It has two cases. Either a term has a Salient transition to a successor, or it has a label transition. And that corresponds to two parts of the coproduct in the functor. Okay, now back to the issue. So this was all known, and our new challenge is how to model a big step semantics and how to connect it to small step semantics. If we look at the big step semantics of the combinatorial logic, one can notice that we cannot just frivolously inspect behaviors of the operands. So if I want to evaluate a composition with respect to lazy semantics, it would make a difference if I check what T evaluates to or not. Because if T is a divergent term, then the left-hand side might converge, while the right will always diverge. So this means that on the level of signature, I need to separate those arguments which are strict and those which are lazy. Otherwise, I will never be able to distinguish these two cases. So this is the first change. In order to basically to make sense of this equivalence claim, another thing is that this equivalence claim also contains a transitive closure of the small step semantics. And in order to model it, we need to define it as a least fixed point of the one-step transition. And to do this, we also need to refine the behavioral functor. It must include a monad. I mean, this is our solution, which supports solutions of the least fixed point equations. So we assume that the signature decomposes into a part for values and part for the computation. We assume a monad, and in the end we arrive at this refined version of the abstract HO GSOS, which we call separated. So it now has a value part, it has a computation part, and it refines properly this more general abstract notion of HO GSOS. I'm not showing you how it converts back to it, but it does. It's relatively easy to see. Similarly, we can define operational model, but now it will have two parts. So values will have their part of the operational model, computation will have their part of the operational model, and we also can define this multi-step semantics thanks to the fact that the monad supports fixed points. And since we introduce a monad, we also can use it not just for solving equations, but we can also model computational effects. Because if we take the monad to be the parsed monad, for example, we can also capture non-deterministic semantics, just like by adding this kind of rules. And then, the last ingredient that we need is the notion of this big step semantics in this equivalence statement. And so it also captured by a natural transformation. So intuitively, this format of natural transformation corresponds syntactically to these rules. So we want to evaluate a term, and we can evaluate strict arguments of the term and then pass the result to some other term, evaluate it, and that result of evaluation is the net result of evaluation of the original term. Right, and okay, so we nearly are done with proving the statement. We made sense of all these ingredients. So we defined multi-step transition, we defined what is a value, we defined what is a big step derivation, but is this equivalence true? Actually, it's not necessarily true, because despite these conditions that we imposed, well, it's very easy to break this equivalence just by introducing rules like this rightmost one, the first one. So make one step of the argument at the top, but then we change the principal symbol at the bottom, and yeah, so this breaks this kind of equivalence, and can be exploited easily to break the equivalence we want. So a solution to this is kind of ban this sort of rules and introduce this condition we call strong separation condition, which I describe on the slide, and it's kind of restrictive. but it's very sensible from practical perspective. This is well-behaved in this condition one expects from the operational semantics. So this kind of situation is not possible. If you're reducing some argument under a function, that function shouldn't change. So, and the main result now, if we start with a separated GSOS, which is additionally strongly separated, and there's a categorical formulation of this in the paper, I just didn't show it. So then a small step semantics uses big step semantics, and they equivalent in the sense that operational models agree. So I guess I don't have time for this. What I was talking about was the lazy version of lambda calculus. There are more examples in the papers. This is particularly interesting one, but I don't have time for this. So if you change the strategy to call by value, something interesting is happening, but in the end it's also covered. So also languages with binders, we can also make lambda calculus, also one of the examples, with a little bit of additional work. So if we look at this standard rules for small step semantic and big step semantics, they are not directly fitting the format we need, because secretly the rule for lambda abstraction alludes to the substitution. And substitution actually is yet another kind of behavior which is implicit in the standard treatment of lambda calculus. But if you want to do this functorially, then you need to make it explicit. This amounts to modifying the value part of the GSOS law by adding this ingredient, which is certain object of substitution action. You need to select the category as a category of certain presheaves. This has been done for the syntax by Fiore and Plotkin in this paper, so we can just capitalize on this work to change this particular part of this framework. Right, conclusions. We have defined the abstract notion of small step and big step semantics, proved the equivalence, and last but not least, formalize this all in Haskell. The paper comes with an artifact with a barcode leading to it. I really suggest you play with it a little bit. It's very simple, but it contains an implementation of it with a bunch of Haskell classes and with examples that I mentioned and a bit more. So here are some further work. Maybe what I mentioned here, which is I found particularly relevant, is so this question of relating the mathematical theory and implementation. So this implementation currently we have is very close to the mathematical theory that I present. Because if the signature is algebraic, then you can model it as an inductive type in Haskell. It's not exactly the same, but it pretty much captures the spirit, and it's essentially the same. But if you have binders in your signature, the mathematical theory, again, it's more complicated, but it's clear. But I'm curious what it corresponds to. I was trying to find some ways to implement it in Haskell. I found the so-called nominal library in Haskell, but couldn't really make use of it. So given that there are lots of experts here in Haskell and functional programming, I would be very delighted if someone reaches out and suggests me a way to implement this kind of meta framework in Haskell in a proper way, so that with the proper name handling and making things that must be a functor, iterative functor, and so on. So thank you. This is it.
Any questions? Yeah.
Just a quick question. I missed the part that when you mentioned if there are non-determinism in the operational rules, how does that manifest in the operational model after the translation?
these are the rules which one can use for non-determinism. And so here in the operational model, I mean, it's manifested as expected. So for a term, I will have a set of successors. So because this T is a power set.
So if you translate this into a Haskell program, how does that run?
Well, I mean, you do it Haskell way. You replace power set by lists.
Oh, okay, thank you.
Hi, I'm Jens Paulsberg from UCLA. Very enjoyable. I have a question. So the way I see your conclusion is that under certain conditions, you can prove that multi-step semantics does the same as big step semantics.
Exactly.
Those conditions, are they checkable? Is that like asking whether this set of rules I give you satisfies the condition of your theorem? Is that something we can check with an algorithm?
Yeah. So there are like 2 degrees of abstraction.
Yeah.
There is like an abstract condition on the in terms of natural transformations, and there is a concrete instance like if they come from these rules, just look at these rules and inspect them, and you will know yes or no.
And so both of these are quite checkable.
Yeah, well, the first one is slightly less checkable and it's also more general because you can have complicated categories and functors without obvious syntactic presentation, something like that. So it's more general, but it's less easy to check.
Right. So if there's any more question, if not, then let's thank Sergey and all speakers again. If I'm not mistaken, there's a poster session, right? Right.